Welcome back to CCCS 111 Introduction to Programming. So today begin we with Chapter 4, C Program Control. And in this chapter, we first talk a little bit more about the while loop that we did at the end of the last chapter, Chapter 3. And then we move on to the for loop today. Later on, that'll be followed up by the switch statement, the do while loop, and with that we'll complete three types of loops available in C, and we'll talk about the break and continue statements. Okay, so what we've seen previously is that there are basically two types of loops in a sense. There's one where you do definite iteration, where you know beforehand how many times you want to go through the body of a loop. And then there's indefinite iteration, where you do not know how many more times you'll go through, you'll run the code in the body of the loop. And that's usually because the number of times you go through the loop or you run the loop depends on data that you'll receive either from the user or from some place that you haven't read yet, like when you're going through a file, reading data from a file. So one thing that counter-controlled iteration structures, so loops that run a fixed predetermined number of times that they have in common is that they rely on the use of a control variable. Indefinite iterations, however, like I said, require the use of a sentinel value of a sense. That sentinel value can come either from the user or can come from the data that's being read or used in a loop. As far as counter-controlled iteration is concerned, there are a couple of elements that they all require. First is a control variable, the name of a control variable. It needs to have an initial value. It needs to change, of course. So that means the value of that control variable either has to be incremented or decremented. And finally, there has to be a final value for the control variable. Now, a control variable can be something as simple as an unsigned integer, and an initialization can look as simple as this one, where we are using an unsigned integer counter and at the same time while defining it, initializing it to the value 1. And if you want to use a while loop for definite iteration, we already saw how to do that, and it can be as simple as this example. One thing that we changed over here slightly is that instead of writing counter is equal to counter plus 1 like we did before, we're using the pre-increment operator over here because at the time when we were looking at the while loop, using the while loop, we had not learned about increment and decrement operators yet. But this is usually, now that you do know it, this is usually how the kind of syntax that you can expect. In this particular example, this is a while loop that will start with a control variable counter set initially to 1, and it will be incremented by 1 in each iteration of the loop, and it'll go until the value of the counter equals 10. So this is one way to run a loop for 10 iterations. You can also split up the definition and initialization into 2 steps like this. And of course, this part over here, the use of the pre-increment operator. This is new in this small short example. You could make this example even smaller by putting the pre-increment operator into the condition of the while loop itself. And that'll save you a line of code after the printf statement. So this works too. Now you can see that these increment decrement operators are pretty handy. And this will do the exact same, perform the exact same actions as the code before. So now we are performing the increment operation and the test on the value of the control variable in one statement, in one expression. However, so we can do all of that with the while loop, with the while iteration statement. But when we know that the number of iterations are counter controlled, a statement that we usually prefer, that you'll see more often used, is the for iteration statement. And this is, like I said, more commonly used in such cases. So there are a lot of details that are being covered in this chapter. I'll go through them quickly. Frankly, they're not that difficult. So let's look at this. Let's start with this example of a for loop. You can see the yellow line highlighted over here. That's really the new thing happening. And this code will do the exact same thing as the previous example in which we were using a while loop. Now you can see in this one line, there's a lot of stuff happening. And among those things, we are initializing, actually defining and initializing the control variable counter, setting the condition or specifying the condition that needs to be true in order for us to continue to iterate. That's this one over here, counter being less than equal to 10, and even the incrementation of the control variable counter that's happening over here. So there are three parts of the for loop that you need to be aware about. This one over here, which specifies initialization of control variable, the iteration condition that needs to be true for us to continue running this loop, and finally the increment or even decrement operation that you want to perform in between iterations of the loop. And these three parts of the for loop are separated by semicolons, not commas, semicolons. Here's a neater labeling of all of that. So we have the for keyword and the three parts that I just mentioned that are part of the for loop all go inside this one pair of parentheses. And like I said, over here we are defining and initializing the control variable. This is the loop continuation condition, which needs to be true for us to continue running the loop. And here are changes to the control variable, usually an increment or decrement operation of some kind, separated by these three separated by semicolons. So in this particular example, the for loop will run for 10 iterations. And the nice thing about the for loop is that all the things that we had to do either before the while loop or in the while loop or inside the body of the while loop, all of that happens in one line, in one very all of that is put on one line. So you don't have to hunt, you don't have to think about, okay, where's a certain variable being incremented, what's it being initialized to. You don't have to hunt or search through multiple lines of code before or after the loop statement. So that's quite neat in that sense. Occasionally, when you use a for loop, you might discover that you wanted it to go for, let's say, 10 iterations, but it actually runs for 11 iterations. Or maybe you wanted it to go for 10 iterations, it's only going for 9 iterations. Usually, so this is a very common type of error that you can end up with, not just with a for loop, but any definite iteration structures, even while loops, do while loops. This is called an off by one error. It's usually, oftentimes, the reason will be that something that maybe should have been less than equal to 10 in the continuation condition, maybe you put in just less than 10 condition, and that will change the number of times your loop will run by 1. So put simply then, the for loop contains, the for loop statement contains these 3 parts: initialization, condition, and increment. And inside the body of the for loop, you can have, again, as many statements as you need. Now, in the example of the for loop that we saw just now, we had only one initialization, only one continuation condition, and only one increment happening. While that is often the case, it is not necessary that there only be one expression that has to be evaluated. So what you can also do is you can have something where you have, let's say, multiple initializations, or where you have multiple increment decrement operations happening in the same for loop. As far as the increment and decrement operations are concerned, so let's say you want to run a for loop, you want to increment the control variable by 1 every time. So that can be written as counter is equal to counter plus 1, what we've been doing so far. You can also write it using this shorter hand notation, or you can use the pre-increment or even the post-increment operators. In fact, whether you use the pre or post increment operators will make absolutely no difference in a for loop. So use whichever you like. Over here, in many of the examples, you'll see the pre-increment operator being used. But I think traditionally, in most places where you see a for loop being used, you'll actually see the post-increment version used. Like I said, it'll make absolutely no difference to the operations. Not in a for loop, at least. And here's an example of something slightly more complex. So, like I said, the statements that you have, the expressions that you have in a for loop statement can be much more complex if you need them to be. One other thing over here, so this is, just want to point this out. You see the placeholder %u being used over here. %u, we haven't seen that as an example. %u stands for unsigned integer. So that's another one you can add to your list of placeholders. This particular example that we've been dissecting again and again, this is the same in flowchart form. So you are initializing in this for loop counter to be equal to 1, checking. This is the continuation condition, checking if it's less than or equal to 10. If so, you go into the body of the loop, print out the value of counter, increment it. This is what's happening in the increment expression, and going back and checking again. And you keep doing that until this condition becomes false, and then you exit the for loop. Here's some more examples. The increment that you perform in the third argument of the for loop statement doesn't necessarily have to be an increment by 1. So in this example over here, for example, this is a loop that will initialize I to 1. It'll keep running until I stays less than equal to 100, and in between we increment I by 1 every time. So this is basically a loop that will run with I equal to 1, 2, 3, up to 100. So 100 iterations. The second example that you see down here, following that, initializes I to 100. It will run as long as I is greater than equal to 1, and it will decrement I, so subtract 1 from I in after each iteration. So in this case, I will be 100 in the first iteration, then 99, 98, 97, until I reaches 1. The next example initializes I to 7 and runs as long as I stays less than or equal to 77. But as you can see over here in the increment operation, I does not increase or decrease by just 1, it is being increased by 7, which means the steps will be I equal to initialized to 7, then 14, 21, 28, 35, all the way up to 77. So this will be 11 iterations if you count them. The one following that initializes I to 20, goes as long as I stays larger than or equal to 2, and over here we are subtracting 2 at every step. So in this one I will start at 20, then it will become 18, 16, 14, all the way until it reaches the value 2. And then we have this very unusual one. You can initialize j to 2 over here, and it'll go until j stays less than or equal to 17, and you're incrementing j by 3 in every step. So over here the values of j will be 2, then 5, 8, 11, 14, and 17. And for the last one, over here, j is initialized at 44, runs as long as j is not negative, stays above or equal to 0, and we are subtracting 11 at every step. So over here the values of j in each iteration of the loop will be 44, 33, 11, 22, 11, and finally 0. And here's another very simple example. In this one, what we want to do is we want to write a program that sums up all the even integers between 2 and 100, both included. You can probably figure out how to do that. Pretty straightforward. You initialize a variable called sum to 0, an unsigned integer. We then define and initialize another variable number to 2, and we keep going as long as number is less than or equal to 100. And because we're only interested in even numbers, and even numbers are at a difference of 2 from each other away, we're going to increment number by 2. And in the body of the loop, the for loop, we're going to add the value of number to sum. When we come out of the for loop, sum will be the number that we're looking for. In this example, if you run this, 2,550. Now, you should also know that it is also possible to write the same program without any statement inside the for loop. I know this sounds a little crazy. But what you can do is that one line of code that you have inside the for loop, where you add number to sum, you can actually put that in the same place as the increment operation of the for loop, which means you have nothing to do inside the for loop. And when you have in some places where you do not have any statement to execute, you can do that in C by just putting a semicolon on that line like this. So this is a kind of an extreme example where you have initialization happening, sure, as expected. You have a continuation condition, but everything else is happening over here in the incrementation section of the for loop. Notice over here that when you have two updates happening, you separated them by a comma. Okay. And not only that, but the initialization of sum to 0 could have been added over here. Could have just added a comma, sum equal to 0. And in that case, this one line of code that you would have outside the for loop, this initialization, you could have also done that inside the for loop. One slightly more interesting example that I want to give you, actually kind of useful too, is this program. So let's say you want to write a program that figures out that if you invest $1,000 at a certain savings rate, say 5% by a bank, you want to know how much money that will grow over a certain number of years, let's say 10 years. Now the formula for that is this. This is the compound interest formula. Okay. Over here, P is the principal or the original amount that you have invested, P for principal. R for rate is the annual interest rate that wherever you're putting your money, a business, bonds, government bonds, something that they're paying you. N is the number of years for which you're putting the money in. And A is the amount that your deposit will be worth at the end of N years. Now this can be done, and you want to print that out for all the years from 1 to N. And you can do that using a for loop. There are two new things happening over here. Everything else should be familiar by now. There's on this line 18 where the actual computation is happening. Let me just jump back over here. You see a new arithmetic operation happening over here that we don't know how to do yet, that I haven't talked about yet, and that is the exponent, the power, n. Now, none of the math operations we've seen, arithmetic operations we've seen so far would let us do that. For that, we need something new. We actually have C actually provides you a function for that, the power function or POW function, which takes 2 arguments. So over here, so let's say you want to find x to the power y. You could do that using the power function x comma y with these 2 arguments, x and y over there. So the base and the exponent. And that's what we're doing. So the principal amount, P, let's set that to 1,000. The rate of return, the interest rate that you're getting, let's say 5%. And then we're printing out just a header, like the name of the columns that we're going to print out. We're going to print out string year and amount on deposit. And after that, we have a for loop, which initializes the unsigned integer year to the value 1 And since we're going to do that for the first 10 years, we're going to run this for loop for 10 iterations until year goes from 1 to 10. In between, we are incrementing year by 1. And in each iteration of this loop, we are computing a value of amount, the amount your investment is worth. And on this side, you'll see the same formula you saw before. So this is, again, P for principal times 1 plus R to the power n. And once we have computed the amount, we print it out over here. We print it out as a floating point number. I'm going to talk about this 21 point F over here in a second. And we're going to print out the year as a 4-digit unsigned integer. Now this power function is not part of the header file that we're already using, stdio.h. This function is included in another library in C, and that library is math.h. And so whenever you want to use this particular function, the power function, you have to include the math.h, the math header file. So now I guess I hope you're slowly appreciating why we put this preprocessor directive hash include at the start of every program. Depending on what functions from which library you're going to use in your program, you will have to include, you'll have to tell the compiler that this function that I'm using is in that library. And that's what the hash include preprocessor directive at the beginning, what that accomplishes. There are many other functions in the math header file as well. So if you run this particular program, you get something like this. So year 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And on the same line, you'll have the amount that your investment will be worth after 1 year, after 2 years, 3, 4, and up to 10 years. Now, I pointed out there's something funny happening over here with the formatting, the way we're formatting this, and the way we are formatting these two strings. So this one over here is basically %4s. What this means is a 4-character long string. 4 characters because the word year, 1, 2, 3, 4, is 4 characters long. The next one is %21s, and that's %21s because we want this to be a 21-character long string, and which this one is 1, 2, 3, 4. You can count it out. These are 21 characters over here. And if you look at the output, the numbers are right aligned. This is not an accident, because each number, each amount that's being printed out over here is being printed out as a 21-digit number. There's 21 digits with 2 decimal digits, these two over here. And the same thing is happening with the year number, right? Okay, so the power function was new, and like I said, what this basically implements is x to the power y. It usually takes double precision floating point numbers as argument and returns a double value as well. If you pass it anything else, don't have to worry. If you pass it an integer in any of these arguments, the function does whatever conversion is necessary, does it for you. And like I said, it's part of the math.h header file. One more thing that I want to point out is the use of floating point numbers or double precision floating point numbers over here. Now, obviously, the numbers that we're working with can be fractions, and that's why it's a good idea to make the amount and principal and rate variables all of types that can accommodate fractional numbers. There's something that you should know when dealing with fractional numbers, and I demonstrated that, I think, in one of the hands-on sections before. So let's say we store the following two numbers. So we have a floating point amount 14.234, which will print out in a two-digit number as 14.23. And we have a second amount, which is 18.673. And if you print it out as a two decimal number, it'll print out as 18.67. If you add these two numbers, the sum will be 32.907. But when you print it out using the percentage 0.2f placeholder, it will print out as 32.91, because this third digit 7 is larger than or equal to 5, which means the second last digit will be rounded to 1. So when you're printing out numbers like this, because the actual value in the variable is something else, has some other digits over here, but you're printing it out as a two-digit number, you may see something like this. You're printing out one number, another number, you're adding them up, also being added up with all those digits. But when you're printing them out as two-digit numbers, the third decimal digit might cause the second decimal digit to round up. So while what you're seeing over here might lead you to expect to see exactly 32.90, what you might actually see can be a little off. Just one other thing about the formatting of the strings, of the numbers actually. We used the format specifier like this for the amounts that we're printing out, 21.2f, which means that the whole field in which the number is going is 21 digits long. Two of them fractional decimal digits after the decimal point. So 2, in other words, is also called the precision of a floating point number. In the examples that we saw, the numbers that we were printing out were right aligned, right? They were aligned to the right. If you want your numbers, or whatever you're printing out, if you want it to be left aligned, you can do that too. Left justified, if you say. And for that, you can just use a minus sign in front of the number of digits that you're specifying. So something like this, for example, this would produce a 6-digit left aligned integer number. This one over here would produce an 8-character long string that is left aligned instead of right aligned.